So I'll probably take that back before the end of this period, but whatever.
I was gonna say, I thought the joke was hilarious. Ha 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 ha.
Yeah, my wife says that's the only way I can get my students to laugh at my jokes is by threatening them or something. Okay, let's get started. We are working on chapter 3.2. We're really only doing some tidying up here. The first topic I want to cover is something we know how to do, but we want to show you with a quotient or a product rule involved, and that is finding the equation of a tangent line at some given point. And then the other thing is a couple of puzzle questions that they've got at the end that look really difficult until you kind of figure out what to do, and then they're kind of obvious, I hope. And then we'll get started today definitely on 3.3, which is we will introduce you to a whole family of functions which are trig functions and how you can differentiate them. That's a biggie here, because the minute you add in trig functions, you get so many more different combinations of product rules and quotient rules, because now you'll be able to do x squared sine x over 1 plus e to the x, right? You'll be able to do all sorts of combinations using polynomials, including square roots, trig, and e to the x's. But that's kind of looking ahead a little bit, maybe too far. So let's do the first one, which is finding the equation of a tangent line. So I'm just going to pick on the equation. And let's suppose we have y equals e to the x over 1 plus e to the x. And we're interested in the slope of the tangent line at 0, 1. Yeah, at 0.5. That's where it would be. Well, the process for finding the equations of tangent lines are pretty standard. You find the derivative. In this particular question, it's not difficult to know when a quotient rule is going to be involved. I mean, you see a fraction, you see a quotient rule. And there is our formula for the quotient rule, which hopefully is just burned into your memory now. You don't need to look it up. Differentiate this guy, leave that guy alone. Leave that guy alone, and differentiate this guy. And on the bottom, you're going to have 1 plus e to the x squared. And then we move on to style points. Well, what I would do here is distribute this, multiply those together. E to the x times 1 is e to the x. Oh, I did it yesterday. I know I did. Or it could have been the day before yesterday. What do you get when you multiply e to the x times e to the x, and you do not get e to the power of x squared? E to the x times e to the x. What do you get?
E to the 2x.
Okay. And the same thing here. And so style points came out relatively nice. So you find the derivative. What you then do is you evaluate it at whatever that guy is. Well, the derivative at 0 is e to the 0, 1 plus e to the 0 squared. E to the 0 is 1. So it's basically that guy. 1 plus 1 is 2, 2 squared is 4. And so I now know the slope of the tangent line is 1/4. And then to finish, use an equation called the point slope equation, which essentially allows you to find the equation of a line with a given slope passing through a point. Right, so the slope m is 1/4, and the point has coordinates 0, 1/2. So it's going to be y take away 1/2, 1/4 x take away 0. And that's going to be y minus 1/2 equals 1/4 x. And then you add 1/2 to both sides, because typically equations of lines are written as y equals, right? In this case, 1/4 x plus a half. And I wasn't intending to do this, but I am now. You can check that you've done it right by using Desmos. Just finding Desmos right now. Okay, let's zoom over to Desmos and check it out. Okay, so the original function, y was equal to e to the power of x divided by, no, gotta watch, there. Now divided by, there we go, and 1 plus e to the x. And then the second guy is our straight line, our equation of our tangent line. So it's y equals 1/4 x plus a half. And we were interested in the point 0.5. So if I zoom in here, would you agree that's a tangent line? You see it, Matt? You see at that point there, 0.5, that guy there? Isn't the curve and the straight line essentially the same? In fact, very often what happens is that before you even get to that point, don't the red curve and the blue tangent line merge into the same? Right. And that's very typical. Tangent lines do that. Now, if I made a mistake, not that I have ever made a mistake, as you know, can you see that they would not be meeting at 0.5? You know, they wouldn't be meeting at that point. If the mistake I went and made was maybe over here, can you see that that's not a tangent line either, right? So if you put in the two things, the original function and the tangent line, you should be able to do a quick check, which is useful in midterms and finals. Obviously, WebAssign tells you when you're right. But I have seen questions where they ask you then to graph it and they give you 4 pictures, right? So you might want to use Desmos in those particular situations. So the next piece of the puzzle is what I've called number 2 here. And these are kind of weird. Give me a few seconds here to find the darn question and get rid of the other stuff. Right, so these are the last 2 questions, 29 and 30. Right, I got 29, let's show you that one. Right, here's 29. And I said they're kind of weird, and I thought I told it to switch them off. There we go. WebAssign's just annoying me right now. Here we go. If you are told information about a function at just one specific point, in this case 2 functions, f and g, if you're told the value of the function and the derivative at x equals 5, and the value of the function g and its derivative at 5, you can then find guys like this. Okay, so let me show you how you get the numerical value for a derivative of a function that you don't even know what the function is. All you know are like a snapshot. So the value of the function at 5 was 1. The derivative at 5 was 3. The value of the function g at 5 is -6. The derivative at 5 was, say, 7. Right. Now, when they write down, what did they do? When they write down that, what they're asking you to do is to find the derivative of the product at 5. And that's what that means, right? Find the derivative of f times g at 5. Now I know how to find the derivative. It's f dashed x, g of x, take add f of x, g dashed of x. Well, at 5, then it becomes these guys. So once you realize that that is saying find the derivative of the product at 5, and then you say, okay, there's the formula for calculating the derivative of a product. That's what it looks like when x is 5. Then don't you simply just plug and chug. The derivative is 3. G is -6. The value of this function is 1. G dashed is 7. And so I would get -18 plus 7. And I would get the answer -11. Are you comfortable with that? How we figured that out? Right. Suppose I asked you to find that guy at 5. So don't think of this as things being multiplied. It might look like it's not. It's actually the quotient of two functions derivative at 5, right? So this is to do with derivatives and functions at 5. It's not to do with this, divided by that times 5. It's not that. Now the formula for the derivative of f divided by g is this one. And f dashed, well, I guess I should put in all the numbers now. F dashed of 5 times g of 5, f of 5 times g dashed of 5, all over g of 5 squared. Okay, now I'll put in the numbers. The derivative at 5 is 3 multiplied by g of 5, which is -6. Take away f of 5, which is 1, times g dashed, which is 7, all over the value of the function, that guy, squared. And that's -18, and that's -7, so that's -25. And -6 times itself is 36. And there is our answer. And the final one of that 3, you got to be a little bit more careful. It's not quite the same as this guy, isn't it? The switch places. Instead of f over g's derivative, it's g on the top over f's derivative, which means this formula here has to be adapted to the new positions. So do you notice f and g here and here? If you switch them round, then everything that's an f will be a g, and everything that was a g becomes an f. So instead of f dashed, you do d dashed. Instead of that guy, you get this. Instead of that guy, you get this. Instead of that one, you get this. And on the bottom, you get this guy squared. Are you comfortable about how I adapted the typical f over g formula to now do a g over f formula, right? It's the same guys, but the f and g have switched positions. So if you switch positions, shouldn't they switch positions in the formula, right? Every f is a g and every g is an f, and that's what I've done. So if you wanted to find this derivative at 5, it would be g dashed of 5, f of 5, take away g of 5, f dashed of 5, all over f of 5 squared. And here goes. G dashed is 7. F is 1. -6, 3 over 1 squared. 7. Well, take away that makes it plus, so you get plus 18 over 1. In this case, the answer ends up being 25. Yeah, it's a little bit different, and I'm hoping that once you figure out what they want, it's not as bad as it might seem. Any questions about that before we move on to trig?
I do real quick because
Go, Izzy, what you
anything
got?
to avoid trigonometry. No, I'm just kidding. Okay, so the first problem that you did was not the quotient. That was the product rule. So there's no dividing it and there's no difference. You're not subtracting.
Correct.
Okay. All right.
So that's the product rules formula.
Okay.
No dividing and everything's added. When you do a quotient rule, things get divided and they get subtracted. It's kind of got both those things, but that's the quotient rule.
Just wanted to clarify. Thank you.
You're welcome. Any other questions? Okay. Well, you're going to be able to get practice in your own homework because there's 2 of those, and actually the one I've done has different numbers as well, probably, so you're going to have that to deal with. So now we're going to have a look at the rest of today, our next section, which is derivatives of trig functions. And this little table is going to get populated by the 6 trig ratios, and then we'll eventually be filling in what their derivatives are. So here goes. I think I'll be colourful. You have a sine x, you have a cosine x, and you have a tangent x. They're called the 6 trig functions, also the 6 trig ratios. Anybody remember the name of the other 3 guys? Sine, cosine, tan, but what's the other 3 called?
One's a cotangent.
Okay, and that goes here. 2 more to go.
You can't.
Okay, so I'm going to put here. And last but not least, who's he?
Isn't it the cosecant?
It is. Now, the reason I've written them in this order is that I'm trying to emphasize that they tend to go in pairs like husband and wife, right? And the sine of x and the cosecant of x tend to go together because the cosecant of x is just the reciprocal of the sine x. In other words, if you took 1 over the sine x, that's what the cosecant of x is, right? And if you wanted to get a secant, it's 1 over the cosine. And if you wanted to find the cotangent, it's just 1 over the tangent. So the 6 trig functions kind of go together in little pairs. Now, can you remember that we did one of those questions where we drew, I can't remember which one it was, but let's say it was the sine function. And we created a sketch of what its derivative would look like. You remember doing that? And when we did it, that's what the derivative looked like. And the derivative is the cosine of x. So here is our first derivative. If you want to differentiate a sine, the answer is the cosine. That's not really a formal proof, but it's the best I can do, right? So, otherwise, you're just going to have to trust me. I'm a mathematician, right? That if you differentiate a sine, you get a cosine. Now, if you differentiate a cosine, you don't quite get a sign. I wish it was simple as that. What you get is the negative of that sign. So the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. You've got those two in your head, right? So we now have 4 more trig functions that we're going to have to find the derivatives for. So that's what I'm going to be doing now. So I'm going to do the tangent function. Well, first thing I'm going to do is annoy poor Izzy. I'm not going to ask her in particular because that'd be unfair. I'm going to ask all of you. Do you know that the tan x can be written in terms of sine x and cosine x? They're called identities. There's lots and lots of trig identities, but there is an identity for tan x. Can anybody remember in sine x and cosine x what the tangent of x can be written as?
Tangent equals sine x over cosine x.
And how do you remember that? You just remember it?
I mean, yeah, it's pretty important, so.
So it keeps on coming up, right? It's a bit like, don't you remember sine squared x plus cos squared x equals 1? Because it's pretty important and it comes up a lot, right? So now that I've established that tan x is this guy, I will now be able to find the derivative of tan x, and I will do it by finding the derivative, right, of that guy. So here goes. It's going to be f dash g take away f of g dashed all over g squared. Now I'm going to be differentiating that. I'm then going to be doing style points. But when you do style points, there's a third rule. Normally there are only 2 rules for style points. Rule number 1, make your answer look like the original. Okay, so don't leave things as x to the half when they should be square root of x's, right? We've done that a fair amount of times. Rule number 2, factor the heck out of it. Shouldn't you factor everything as much as possible? And rule number 3, I have mentioned it, but we've never needed to use it until now. Rule number 3 is the ugliest one of the 3 rules. Use trig identities to try and make the thing simpler. Sometimes you're able to do that. Now that means you're going to have to remember some of the basic trig identities that you've done in the past. Like you're going to have to remember that sine squared x plus cos squared x is 1, you know, things like that, right? And you're also going to have to remember that 1 over sine x can be written as cosecant x and things like that. So it's going to jog some memories. Right, here goes. Differentiate the top, you get cosine x times leave the bottom alone. Take away, leave the top alone, which is sine x, and differentiate cosine x, which gets you negative sine x. All over the bottom, which is cosine x squared. So far, so good. Now, cosine x times cosine x is written as cos squared x. You all know that, right? That's how you write cos x times itself, cos squared x. And a negative sine x times another sine x gets you plus sine squared x. And the whole thing is going to be over cos squared x. Okay, style points is now kicking in. Is there any identity that you know of from your 142 world that you could use to make this thing simpler?
Yeah, the whole expression is equals secant squared x, because the top equals 1.
Yes.
Divided by cosine squared x.
The top is equal to 1. And just like you said, one over cosine is a secant. So 1 over cos squared is secant squared. We consider this the simplest form. we have used identities to make it simple. And you might say, well, there's not an awful lot of difference between that and that. There is a difference. Isn't that a fraction and has a 1 in it? And isn't this not a fraction and it doesn't have a 1 in it? So if you're being really fussy, isn't this simpler? Right, there's less to it, which means we have our first answer. Now, what you would typically do is memorize these 6, because that, trust me, is just easier on your brain once we've done all 6, that you just memorize them. Otherwise, when you get derivatives, aren't you going to have to do all this every time you want to do it? Or you might say, well, I could write it down. Yeah, you could, I guess, but there are certain things worth memorizing, right? They just are. It helps your thought process. Do you know, if every time you do something, you have to go and look at a piece of paper to find out what it's equal to, doesn't that break your line of thought? If you just know the answer, oh yeah, I'm going to go A, B, C, D, E. I'm not going to go A. Okay, I'm going to have to look that up because I can't remember it. Okay, I've got it. Where was I now? Oh yeah, I'm 92 B. Oh, wait a minute, I've got to look that up as well because I haven't memorized what that is. Okay, I've got it. And you see that? Well, takes too long, screws up your thought process, right? And we want to be good mathematicians, so just memorize these guys. Right, back to school. Let's see our next fella. We are going to now do the derivative of cosecant x. And I'm going to have to write it down. Pretty much the same strategy that I use for tangents. You write it down using sines and or cosines. Can anybody remember what the cosecant of x is using sines or cosines? It only uses one of them. What is the cosecant of x?
1 over something.
It is. Doesn't it sound like it should be 1 over cosine? Cosecant x. Doesn't it sound like there's a cosine sound in it? I wish it was a different name, but it is 1 over sine. Now, in this world, I'm going to call the top f and I'm going to call the bottom g, because anytime you have a fraction, oops, that's still y, by the way. Anytime you have a fraction, doesn't that mean a quotient rule, right? And so it's going to be f dash g, take away f of g dashed, all over g squared. And so if you differentiate the number 1, what do you get? What's the derivative of 1?
0.
So it's going to be 0 times, leave the bottom alone, take away, leave the top alone, and differentiate that guy to get cosine x. And then you take this guy, which is sine x, and you square it. And that's nothing, and that gets you negative cosine x. And on the bottom, you get sine squared x. And now things get quite messy. We are going to use identities, right, to make that look prettier. And it's not, I don't think, that obvious how this is going to work. But if someone could tell me how they think it's going to work, I'd be really happy and pleasantly surprised. Otherwise, you're just going to watch the magic, because it's kind of magic.
Sine squared x equals negative cosine squared x plus 1.
Oh, interesting thought process. Don't go
Then
there.
you could, well, you can then, what's the magic rule?
The cosines won't cancel with the cosines, if that's what you're
No,
thinking.
no, because there's the 1.
There's the 1. But it was a good thought process. None wrong with that. I like the way you're thinking. Any other ideas?
Isn't cotangent the inverse of tangent? So could negative cotangent times sine x?
Okay, let's see how that's going to go. I'm going to rewrite this. Which I'm bringing in what you said, the cotangent. I'm just maybe taking it slowly. This guy is him. Would you agree? Cosine minus 1 on the top, that all works. Sine squared split into 2 because it's multiplying, that works. Like Harman was saying, isn't cosine over sine called something? Can you remember what cosine x over sine x is called? Harman mentioned it. What's it called?
The cotangent.
Called the cotangent. And isn't 1 over sine x a cosecant x? So there's your answer. Negative cosecant x cotangent x. Next one. Only 2 to go. Okay, tell me how to write secant x using sines or cosines. It only uses one.
One over cosine.
Isn't this going to be very similar to how we did the cosecant, right? It's going to be very similar. And it will have a similar looking answer as well. Top will be f, the bottom will be g. So it's going to be f dash g, take away f of g dashed over g squared. Okay, if you differentiate 1, you get 0. Leave that guy alone. Take away, leave the top one alone. And if you differentiate cosine, you get negative sine. And on the bottom, you get that guy squared. Well, that's nothing. That's a negative, so is that. So you get a plus. I guess you don't really need to write plus, but I've done it now. Okay, sine x over cos squared x. Similar process, different looking answer, right? With a similar looking problem here, right? So a similar process. Can you figure out how to split sine x over cos squared x in such a way that we can simplify it? And typically simplification means no fractions when you're finished.
We can go for secant x and tangent x.
Okay.
So we split it for 1 over cosine and then sine over cosine.
You comfortable about that? What we did? Sine x on the top, right? 2 separate cosines multiplied on the bottom. That guy is called secant. And this guy is called tangent. And so the answer to what is the derivative of secant x? The derivative of secant x is secant tan. And that is number 5 done. Any questions so far? A lot going on? A lot of cobwebs getting moved? Which is a good thing. Last one. Same process. Turn things into only sines and cosines. This time you use both. What is a cotangent x using sines and cosines?
Cosine over sine.
Great. So won't this one look very like the tangent, right? The same kind of process that we did with the tangent. So top is f, bottom is g. The derivative then, f dash g, take away fg dashed over g squared. The top guy, if you differentiate a cosine, you get a negative sign, and you leave the bottom one alone, which is sine x. Take away, leave the top one alone, which is cosine x, and times the bottom. Well, the derivative of sine is also cosine x. And sine x squared. Now, a negative sine x times another sine x gets you negative sine squared x. And these two guys get you negative cos squared x. And this guy is called sine squared x. That's looking okay. Let's just do it one step at a time. Negative sine squared x, negative cos squared x actually can be written down as something a lot simpler.
-1.
Right. You're more used to being sine squared plus cos squared is 1, right? That's what you're more used to saying, right? Sine squared plus cos squared is 1. But isn't negative sine squared, negative cos squared basically just pull out a -1 and you've got the same guy? So what that gave me is -1. And now, one last line. We have to find a nicer way to write -1 over sine squared x. Well, the negative's easy, I just put it there. But 1 over sine squared x, what is that guy going to be called?
Cosecant squared x.
And we are finally finished. All 6. There they are in all their glory. So let me try and give you some clues to how to help you to memorize these ones until you just get that used to them. It's second nature. The first 2 you've just got to remember, you know, like you remember words in French, right? You just remember, you know, 1 is un and 2 is do, whatever, right? There's not really much you can say about that. First trick, half of these are positive and half of these are negative. So one of the most common mistakes people do is they get the sign wrong, right? They make it a plus when it should be a minus or vice versa. So here's a way to remember. If the original starts with a C, right? If the original thing starts with a C, the answer is negative. Right? So if I'm going to differentiate a cosecant, I know it's negative something. If I'm going to differentiate a cosine, it's negative something. If I'm going to differentiate a cotangent, it's negative something. So that's how you keep track of the, you know, is it positive, is it negative, right? So if the original starts with a C, the answer is negative. Got that little trick? It's a little trick. At least it'll help you get the signs sorted out. And the other ones are not that easy to remember, but there are patterns to it. And let me show you some of the patterns, at least the way I look at it. Everyone's brain works different. But I look at the derivative of secant and cosecant. And what I notice is that they have a pattern, and the pattern to me is oppositeness. So he's negative, she's positive. This one has a cosecant. Well, the opposite of a cosecant is a secant. The opposite of a cotangent is a tangent. You see what I'm saying about oppositeness? So if I can only remember this one, if I remember that oppositeness rule, don't know what else to say it, right? I can probably figure out what that one is. Now that oppositeness also works for the tangent and the cotangent. I'm positive, so you're negative. I'm a secant squared, so you're a cosecant. So when I talk opposites, sines and cosines are opposites, right? Secants and cosecants are opposites. Tans and cotangents are opposites, right? Okay. So a married couple is a sine and a cosecant, right? They're together. Opposites are their x. So who tangent used to be married to was cotangent, right? The exact opposite of me, right? So there's two different types of relationships, right? Husband and wife, right? That's like sine and cosecant and cosine and so on. And then the opposite ones. No, that's a bit of fun, but yeah, try and put stories into things. That helps me sometimes. Just make up daft relationships between things. So do you know that x to the power of 0 is really lonely? Because there's only one of them. That's how you remember x to the 0 is 1. You just make up a little silly story like that. Oh, x to the 0 is lonely. There's only one of them. And then it helps you remember, right? So whatever it takes to do that. Has anybody who may have done calc in high school, did you ever come up with little tricks that helped you that you want to share on how to remember these 6 guys? Because they are kind of big and I want you to try your darndest to memorize them. Did anyone figure out any ways of making it work? Nothing you want to share? Okay. Well, it's a perfect time for us to finish. So put your last name down for attendance. And tomorrow we will be doing nothing but product, quotient rule, and just general trig derivatives. And oh gosh, you've done it again. Izzy, I've told you before, stop doing that. Right? Okay. Trig is your friend, right? Husband and wife, they're nice people, you know. Give them a chance, right? They can become your friends. Okay, that's it. I'll hang about for any questions. Bye-bye, guys.
Thank you. Goodbye.
Bye-bye.
Thank you.
Right, you're welcome.
I had a question on problem 13 in the web assignment again.
13.
Yeah.
Let me find, is it the square root of x e to the x guy?
Yes, it is.
Okay, let me go through it pretty quickly. Hopefully. I think it's going to be style points that's going to get you. That's my prediction anyway.
It probably is. I sent you an email on it, like literally when we were waiting to start class.
Oh, I haven't had a chance to say it. So let's I'll call it y equals. So x to the half e to the x, right? That's your start point. It's definitely a product rule. I don't think there's any disagreement about that. So that's going to be f dash g plus f of g dashed. Now, if you differentiate this guy, you get 1/2 x to the negative half, right? That's the power rule. Multiply by the power and reduce it by 1. Leave that guy alone. Plus, leave this guy alone and differentiate e to the x, which happens to be e to the x. And this is where style points kicks in. There is a common factor of e to the x. That's not a problem. What's the problem is that there are also an x to the power of somebody as a common factor. Now, you're probably quite comfortable when it's an x cubed and an x squared, right? You can say, oh yeah, common factor of x squared, right? When you have fractional powers, and in particular, if one of them is negative, then it's a little bit harder to do, but it's still a common factor. And the rule when you have 2 powers of x is the common factor is going to always be the smaller of the two. So the common factor is x to the negative a half. You with me so far?
Yes.
Right, now, one of these two is going to be easy, the first one. Used up, still got a half. You comfortable with that one?
Yes.
Now the weird one. Used up, x to the half, use up, take away, negative a half. So you've got a half power, and you're going to take away from it a negative a half power, which essentially means you're going to add it, so you get x to the 1.
Yep.
Oh, things are looking good. Now, that's e to the x, 1/2 plus x, over e to the x to the half.
Yep. That's what I had as my first derivative.
Okay. And as a style point, it looks like that, right?
Yep. Yep.
Okay. So now we have to move on. And I'm going to rewrite the first derivative back to looking like that. And the reason why I want to do it that way is that it's much easier to do a product rule, even if there's 3 bits to it, than it is to do a quotient rule where the top itself is a product, because then you have to do a product inside a quotient rule, and you normally lose something somewhere when you try and do that. Now, because of that, that means I'm going to do, for want of a better term, a triple product rule. And so the second derivative will be f dashed gh plus f g dashed h plus f g h dashed. Are you comfortable with that formula? Right.
Oh yeah, 100%.
So, let's go then. If you differentiate this guy, you multiply by the power and you reduce it by 1. And then you leave the other 2 things alone.
I can already tell where I went wrong. I didn't have a negative there at the half.
Oh, okay. Then we might not need to go further, or do you want me to just go to see where it turns into?
Yeah, I still want to make sure I don't have any more issues.
Okay, so then I'm not going to have enough room, so I'm going to just write the guys underneath each other because I don't want to crunch things.
Yeah,
So
that's
when
fine.
we go to the next one, it's going to be plus x to the negative a half times the derivative of the middle guy, which is still e to the x, and then leave the third one alone. And then in this one, it's leave the first one alone, leave the second one alone, and differentiate that guy, which basically just gets you 1.
Yep.
So we have got this guy plus this guy plus this guy, right? And I'm looking for, imagine it's a big long row. I'm looking for common factors. So they all have an e to the x in it. So I'm going to pull that out as a common factor. They all have a power of x in them.
Yeah.
And the power of x that I'm going to use is the smaller of the 3 choices.
Which is the -3 half.
Great. So now all we have to do is figure out what's left over in each of the 3 pieces. And we should be done. Now, from the first one, used up, not used up, not used up. So you've got a negative a half and that. So you actually get that piece and that piece. Be comfortable with those 2.
Yes.
Right. Now, middle one, used up, right? Not used up. And this guy, well, negative a half, take away -3 halves. Negative a half, take away -3 halves. That's negative a half, add 3 halves, which gets you x to the 1. And that guy, right? Because that wasn't used up. Now this one, e to the x is used up. 1/2, take away this fella, right? 1/2, take away -3 halves. So what do you get if you do 1/2 take away -3/2? Well, you have 1/2 add 3/2, which is x squared.
Okay, good.
Now, e to the x is good. Bring that downstairs, distribute. I get -1/4 minus 1/2 x plus 1/2 x plus an x squared plus an x squared. That guy in the bottom becomes him. What we got here, 2x squared. Oh, that's interesting. Those two cancel out, -1/4. Let me check that. So what question was that guy?
That was problem 13.
13. So these are with my numbers. So you may have got slightly different version, but hopefully. Oh no, they didn't change it. That's good.
Yeah.
And I was just wondering, there is a mistake here. So what did I do wrong? Because that's right, and that is right. But the x's didn't disappear. And I'm not sure why they didn't disappear. Because it looks quite obvious that they kill each other off here. And there are no more x's left unless I missed an x somewhere. This looks right.
It does. It looks a lot better than what I had.
But it's not their answer.
Yeah.
No, I'm totally happy with my method. I'm not happy with my answer, not agreeing with them. Because normally when that happens, I've just forgotten a plus somewhere, right? Or I missed a 2. And that might have happened, but this here is correct, right? This here is correct. So I know that it had to be in this half of the process. So I guess I'll do a quick scan through. Is that -1/2? Yes, it is. And if that's -1/2, the other two have to be positive. There's no more negatives. Right?
Yep.
There's nothing in those two that's ever going to make a negative appear. Right? There just isn't. I wonder if they're wrong. I don't like that. I don't like that at all. I'm looking at their solution. I mean, they just tidied that up. That's nothing. Okay, they separated it. That's okay. That doesn't make any real difference. Just thinking out loud here. They did get them to join. That's weird. I mean, they did this thing a different way. I mean, that's fine. They can do it any way they like. They just essentially they combined these two together by multiplying them through and just having an f and g. That's all they did. So they made this guy here a half x to the -1/2, and they made this x to the +1/2, and they did a product rule. There's no reason in the world why that should cause any great issues. And yet it did. Yet it did. Let me see if I can find some mistake in their working. Okay, that's good. That's good. I can't see any mistake in their version of how they did it, yet it's not my version. So there's a job for you to do. Figure out why I didn't get that guy. Oh. Yeah, I'll write it down the way we would see it. It would be x squared plus x minus a quarter over that guy. And I can tell you right now, I know what the problem is. Those two guys need both to be pluses to get that. So figure out why that's not plus a half.
Okay.
But that's for you to do. I have customers.
Yep.
We have to
Done
do
that.
it. Brendan, tell me tomorrow if you figured out what I did wrong, right?
Okay, sure.
Okay, what you got, Josh?
I'm stuck on question 10.
Question 10. Right, let me get your version this time. Are we talking about product and quotient rules?
Yes.
Okay. Okay, almost there. Okay. Looks like you got a sign though.
Sorry.
I'm just talking out loud. It looks like you've got a sign wrong. Looks like somewhere in your process. Right. So there's this guy that we're starting with. Agreed?
Yes.
So what I'm going to do here is just replace that with that.
Okay.
So product rule. So the derivative will be f dash g plus f of g dashed. Now, if you differentiate this guy, you'll get a 1 plus a 9e to the t. And then you leave the second one alone. Then you leave the first thing alone. And you differentiate that guy. And you'll get 1/2 t to the negative 1/2. You comfortable with that?
Yeah.
Right. So what I'm going to do now is essentially distribute everything and then see what we get. So this guy gets you t to the half, 9t to the half e to the t, plus, well, if you multiply this and this together, you get 1/2 t to the half. If you multiply this and this together, you get 9/2 t to the negative 1/2 e to the t. So far, so good?
Yes. Yeah.
Okay. I have got this guy and this guy. So that's going to get me 3/2 t to the half. Then I have this guy. And finally, I have this guy.
Okay. Yep.
And here is the kicker. Style points. You pulled out t to the half. Right? That's what your answer says. But that's not actually the common factor I'm going to pull out. They do all contain a power of t, so that was the right thing to do. But when you have a choice, you don't pick, well, in this case, you pick the half. You don't just pick the half. You pick whatever is the smaller of the two choices. And negative 1/2 is actually the smaller of the two choices. T to the half, t to the negative half.
Oh, okay. Maybe that
Now,
was part of the problem.
right. Now, this guy at the end is the only one of the three that's easy. Right? Used it up, done. Now we get to the sneaky ones. If you want to pull out a common factor of t to the negative a half, what you're essentially doing is removing negative a half from each of the powers. So what you've got is a half, take away negative a half, which is a half plus a half, which means you get t to the 1. Now, if you want to check it out, multiply that by that and you get this guy, right? So 1/2, remove negative a half, gets you t to the 1. So those are the two weird ones. Now, 3/2t, 9t e to the t, and 9/2 e to the t, all over t to the positive a half. And now you can have